All right, class. This is the second part of 19B problems. This is number 56 and 74. So let's take a quick look at this. Using the data from Appendix C, calculate the delta G standard for each of the following reactions. Indicate whether the reaction is spontaneous under standard conditions. So these are all going to be the delta G standard. So we can use the Appendix C to get this information. So if I'm going to do this, let's take a look at letter A. Now letter A is the hydrogen plus chlorine yields hydrochloric acid, or hydrogen chloride in this case. So if I'm going to do this, here's what I know already. The nice part about this is every time I have an elemental, a reactant or a compound or a product that's elemental, that means that it's going to have a delta G of 0 and 0. So it's only this one that we need to work on. Remember that it's always the number of products minus number of reactants, but our number of reactants is going to be 0 for this. So whatever our products are, but we also must take this 2 and multiply by what do we get for delta G. So that's what this is going to look like here. So my products minus reactants and the 2 for the coefficient in front of hydrochloric acid or hydrogen chloride. So in this case, for 56, this number is a negative 95.27. Okay, sorry, I have to squeeze that in there. Let me see if I can make that look a little bit nicer. 95.27 kilojoules per mole. Okay, so that means 2 times that minus 0, because that's a 0 and that's a 0, means that for what I have here is a negative 190.5 kilojoules per mole. And because it's a negative, that means that this is a spontaneous procedure. It happens without outside intervention. Okay, so I'm going to give you a chance to do this one on your own. For part B, I have this here just to make sure that we're all clear. Like, here is the delta G and the delta G for hydrogen and the delta G for hydrogen chloride. So those are the numbers that I'm using to find this. Remember, products minus reactants. All right, let's continue on. I'll do one more example of that. So let's take a look at letter C. So for letter C, again, I'm doing the same thing, except this time here, that hydrogen is the only thing that is 0 in this case. So we have 2 times, well, let's start off with our products minus reactants. Okay. In this case here, my products is N2H4. N2H4 has, where are we at here? Let's take a look. N2H4 is 159.4. So that's 159.4 kilojoules per mole. That is the only product I could do my plus 0 for this, and I'm not multiplying by anything because I don't have a coefficient there. And then I subtract that 2 times, because of that 2 there, NH3, that's a gas, NH3, that's a gas, negative 16.66. So let's go back here, negative 16.66, like that. So I multiply those 2, and what I get, because this is a negative and this is a negative, I get those adding up to a plus, and I get a plus 192.7, and that's kilojoules per mole. And because this is a positive here, that means it's a non-spontaneous. That's how I do all of them. So we're going to do this calculation quite a bit, actually, because in 74, I have a similar situation where it says consider the reaction. Here's our reaction of H2 and F2, 2HF. Using the data from Appendix C, calculate the delta G standard at 298. So this is just one of those questions where I go back through. I know this one's going to be 0. I know that one's going to be 0. Let's take a look at what HF is. So HF for delta G right here is negative 270.7. So I have my products minus reactants. There's a 2 here, so that's 2 times negative 270.70, like that, and then subtract my 0 and my 0 from that side, and what I should get is a fairly large minus for my delta G. So it looks like it gets something like 41.40 kilojoules per mole. Okay, so that's my answer to A. Now, what am I doing for B to get a non-standard? Calculate the delta G. If the reaction mixture consists of 8 atmospheres, 4.5 atmospheres, and 0.36. Okay, now let's go back to this again. Oops. There we go. 2HF. Now, why would they give us this? Well, this isn't equilibrium. Okay, so we're going to calculate the delta G at 298 if the reaction mixture consists of, and now I have these amounts here. We know that the Kp is whatever the pressure of HF squared over the pressure of H2 times the pressure of F2. Okay, so that means that I'm putting in here 0.36, squaring that, divided by 8.0 and 4.5, like that. So what is that value? Now, let me grab my calculator, plug this in, find out what that is. So 0.036 squared divided by 8 divided by 4.5 equals 0.0036. So that's the Kp is equal to 0.0036. So what is our equation? Our equation for this, give myself a little bit more room, is going to look like delta G standard equals delta G times, let me make sure I know what I'm talking about so I don't give you the wrong information, plus, that's why I check, plus RT natural log of the Kp. And that's it. So now we know what this was, 41.4 kilojoules, okay, plus, then we know what RT is. R, in this case, we're going to use the 8.314, and because we have kilojoules, and this is in joules, I'm going to move this over 1, 2, 3 places. So point, let me rewrite that. 0.008314, like that. That's our R value here. I'm going to multiply that by 298 Kelvin. And I'm going to multiply that by, oh, come on, there we go, the natural log of 0.0036. And when you get all of that, you should end up with negative 555.34 kilojoules, just kilojoules, not per mole. Okay, that's it. See if you can confirm my calculations and get the same answer that I did.